So now that we've become acquainted with n-dimensional space and we've considered coordinate transformations from one set of n coordinates to a different set, and we call them the unbarred coordinate system x1 to xn. That was our first coordinate system, and then we thought about transformations, and we're going to think about transformations to a different set of coordinates. Let's call it x1 bar to xn bar. And now we've thought about the coordinate transformations. At this point, we're going to really think about what scalar fields, what vector fields, and what tensor fields are. And these quantities are all defined in some way in terms of how they transform under changes of coordinates. So if we think first about scalar fields. So scalar fields, so a scalar field can be called t, and it will take the coordinates that describe a point in space, and it will throw back a number. So this is some function that takes the values of the coordinates and throws back a number. And a scalar field is defined by the fact that under a coordinate transformation, this number is invariant. So we can write that this is equal to t bar, so some function of the barred coordinates. Okay, and in general, note that the functional forms may be different. So t, this function is maybe different than t bar, but the number that it throws out will be the same. Okay, so for an example, we can let's think of a three-dimensional coordinate system, x, y, and z. We have a vector r. Then we can ask what the length of this vector is. So the length of this vector is just a number. And this number, this length, better not change if we change the coordinate system that we choose to measure it. Okay, so in our unbarred system, let's call x1, x2, and x3. So this is our unbarred system. This is x, y, z. And here the length of our vector is just equal to the square root of x squared plus y squared plus z squared. Okay, at this point. So x plus y and z. But we could equally choose a different coordinate system, the x-barred coordinate system, and let's make our x-barred system the spherical polar coordinates. So we have an x bar 1, x bar 2, and x bar 3, and this is our r, theta, and phi. And here, in this coordinate system, the length of our curve is just given by r. Okay, so the functional form is different, but the length, if this is an arrow of length 1, it will be an arrow of length 1 whether we use a Cartesian coordinate system to measure it or a spherical polar coordinate system. So scalar is invariant under transformation of our coordinate system. Now that we've defined what a scalar field is, we get to the really interesting part, and this is our first look at vectors and vector fields, and hopefully you'll be surprised to learn some information you didn't already know about vectors. So this is vector fields. So let's think about a vector A, and let's give ourselves a two-dimensional coordinate system, x, y. And let's think about, so this should be going to the origin. Let's think about basis vectors. And let's call the one in the x direction E1, it's a vector. And let's call the basis vector in the y direction E2. Now we can construct this vector A, as you know, from its components and its basis vectors. So a component can be found by thinking about shining a torch, okay, and looking at the length of the shadow cast by the vector. Okay, so if we shine the torch in this direction, we get a component, so the length of the shadow, A superscript 1. So our vector A can be constructed by going A superscript 1 along x, so E1, plus, and let's shine our torch this way now, and we get a length of a shadow cast called A2, superscript 2, plus A2 in the y direction, which has a basis vector E2. Okay, so you know all of this. Okay, so the important point to note is that if we look at the torch shining to the ground, we can define how this is oriented in two different ways. So the first is that we could say the torch is shining perpendicular to the x-axis. But we could equivalently say that the torch is shining parallel to the y-axis. But let's consider another case. So we've got the same vector A, but now let's have a coordinate system in which the coordinate axes are not orthogonal. So let's call it x bar 1. And let's call this x bar 2. Okay, so unlike in this case, where shining a torch shining a torch to the ground could either be described as being perpendicular to the x-axis or parallel to the y-axis. In this case, the length of the shadow cast by shining a torch perpendicular to the x-axis, this x bar 1 axis, is not the same as the length of the shadow cast as shining a torch from shining a torch parallel to the opposite axis, so this x2 axis. Okay, so let's make that clear. So let's shine our torch parallel to the x bar 2 axis. Okay, and we produce a shadow of this length. We call it A superscript 1. And this is different from the length of the shadow cast by shining the torch perpendicular to our x1 axis. And the length of that shadow we will call A subscript 1, just to distinguish the two. And the same thing happens with the component in the other axis. If we shine our torch perpendicular to the x2 bar axis, then we get a length of a shadow that we call A2. Okay, so it's a component in the second coordinate. Or if we shine a torch parallel to the opposite axis, then we get a different component. And that's this A2. So you may say, so what? But how do we reconstruct our vector? What does our vector equal? It's a component times a basis vector plus a second component times the basis vector for the other direction. Okay, so let's put our basis vectors on. This is E1 bar, and let's have an arrow because it's a vector. And the basis vector in the other direction is this guy, E2 bar. So we want to reconstruct our vector A, and we want to go some component along the E1 bar direction plus some component along the E2 bar direction. Okay, and now you're faced with the choice of which component do you use. Do you use the A superscript one or the A subscript one? So which component? Okay, so at this point we learn that there are different representations for vectors, and it turns out that the correct thing to do is use the superscript ones, A1, A2, with our basis vector E1, E2 bar, and we have the plus. Okay, so this is correct. A does not equal A1, basis vector E1, plus A2, so you can see this by just trying to do this. So if you go this much along X, so this much along X takes us to this point. Okay, so that we go A1 along X, and then X1, and then A2, which is this length, along E2, okay? And this constructs something which is not the same as our vector A. So the components with the superscripts, the A1 and A2, superscript 2, these are known as contravariant components. And the components with a subscript, these are known as covariant components. And the names contra and co, so contra means against and co means with, they're named as such because of the way that these components transform under coordinate transformations between different sets of coordinates. And that's what we'll look at next. And we'll find that these covariant components, although they can't reconstruct our vector in this way, we'll find that we just need to think a bit more carefully about how to use these to reconstruct our vector. And the solution will be thinking about something that we've taken for granted so far, and that's the direction of our basis vectors. Okay, so we'll study basis vectors, and we'll find that there are different types of basis vectors. And the different types of basis vectors go together with the different types of components. Okay, so stay tuned.